Hello, and welcome back from this very atypical spring break. So, to address a few things, this is an unusual situation in the university closing to the public and students not being allowed to come back from spring break due to the COVID-19 or coronavirus pandemic. Now, certainly, this is unprecedented in my lifetime. Never seen anything like this, and as such, we're just going to have to do the best that we can in navigating through a very fast turnaround to going from traditional classroom instruction to 100% online instruction. And certainly, I expect this to change, at least the format I take, based on whether or not I find additional tools which might be helpful in delivering things like office hours online, things in support of you all to be successful. Now, certainly, the screencasts, as you're listening to now, will be posted. That's the goal, to be posted online on the YouTube channel for screencasts for this class 2 days before the scheduled class meeting. Now, for the first class, completely online, it's a little bit late. I've been spending time trying to get other tools tested and online, and I appreciate those students who spent the bit of time to help me test it out. So these will be pre-recorded and posted 2 days before, and the idea is for you to look at this screencast and listen to them in their entirety. And then we will certainly also have a live class, and these live classes will meet at our usually scheduled time, Tuesdays and Thursdays from 9:30 to 10:45 in the morning. And these live sessions will not be a repeat of the recorded screencasts, right? So it will be important for you to do your best to look at the screencasts, view them in their entirety before the live classroom at 9:30 in the morning for this class. And so they won't be a repeat, and what I'll do is focus on quite a number of key slides and use that opportunity in WebEx to do whiteboard type of explanations to really answer your questions and address the sort of things that people would usually come to me or ask me or query me about in person. And so the WebEx session will be recorded, and they will also be posted alongside, well, not really on the YouTube channel, but the WebEx sessions will most likely be posted on the Blackboard in some fashion. I will link to the videos from my Dropbox. I have purchased Dropbox subscription. So it'll be really important for you to attend the class. If there are, extenuating circumstances, then I certainly will be flexible in light of what has recently happened. But if they'll be recorded for you to look at, but they're not really a substitute for attending. But please try your best, and I certainly understand you all have varied internet connectivity and varied time, in your residences and stuff like that. So the goal is to support two different models. One, we can do it live from the WebEx session, but also acknowledging based on the connectivity you have, it might be easier for you during certain periods of the day to download this content and then view it elsewhere. So I'll support both the synchronous as well as the asynchronous as it pertains to the live classroom sessions. So lastly, this can all be stressful. We all have family units of some sort, and I fully acknowledge that certainly in the context of what's going on, it can affect different people differently. So please let your faculty know how you're doing, and there are resources through the university. Let me know if there are issues. Let Dr. Rasamni know if there are any issues with this class or any other class. So certainly all of the faculty have been, discussion has happened in trying to, accommodate students in the varied circumstances through no fault of their own that have arisen due to this COVID-19 pandemic. So with that, why don't we try to return back to some semblance of normalcy. Administrative. So please watch the following video on YouTube. It talks about Kmeans clustering, how it works. It is very well done. And then we also have some reading. There's the URL for the reading, but I've posted it on the Blackboard. In that reading, you'll be looking at sections 8.1 through 8.1.2, which is covered by pages 490 through 494, and then section 8.2 through 8.2.1, which is covered on pages 496 through 506. Okay. So certainly at this point I would say any questions, but certainly I can't say any questions because I'm sitting here at my desk in the home office, which is also very weird for me to be doing it this way. Nonetheless, where we last left off, we talked about the PLA algorithm, and we gave the framing example of looking at a two-dimensional feature space where the first feature corresponded to the annual salary, and the second feature, represented by the vertical axis, corresponds to years in residency. And so we looked at a model or a hypothesis at a class of functions that would be good for separating those points representing customers, each point, that are good credit risks who you would extend credit to. Those are the green points. And the negative examples, the bad credit risks, those who you would not extend credit to. Those are the red points. And so we take a line, and the equation for a line, y equals mx plus b, as we discussed, has two parameters, m and b, where m is the slope and b is the y-intercept. And we also we can generalize that as weights w. Instead of using alphabetic characters, because you only have 27 characters in the alphabet, you generalize that using W1 and W2, because by using an integer subscript, you can have as many different governing parameters for the model as you want. And so here on the right-hand side, we see this yellow box. And this yellow box, any point we select within this yellow box has a projection along the horizontal axis, which is the b-axis. So every point along this b-axis represents a different y-intercept, and every point along the vertical axis represents a different slope. And so for every single point in this so-called hypothesis space, it defines the two parameters, y, m, and b, that collectively define any possible line. So a line on the plane has two weights, W1 and W2. We talked about that. You can talk about a so-called linear model in 3 dimensions that would certainly have 3 weights, W1, W2, and W3. If you were to generalize this in arbitrary d many dimensions, you call it a hyperplane. So in 2 dimensions, as we see here, a linear model is called a line. In 3 dimensions, a linear model is a sheet, it's a plane. And in arbitrary d many dimensions, your linear model is called a hyperplane. So we had the framing example where we last left off, and we talked about the credit classification problem. And we have an input vector, and these are the attributes x1 through xd, d many attributes or descriptive features that collectively describe a particular credit applicant or customer of the bank. And so we have a corresponding linear model, and for each feature, there's a corresponding weight. So we have W1 through WD corresponding to that D-dimensional feature space representation describing a customer. We also introduced this idea of a threshold T, and the threshold T is the score associated with approval. So this is your litmus test. We're going to take a weighted sum. So we're going to say x1 times w1, and we're going to add that to x2 times w2, x3 times w3, up to and including xd times wd. And so we add all of those together, and it's going to result in what we're going to call our score. And then we check to see if that score exceeds the threshold. And that threshold T is a score associated with the minimal approval. So we input our customer data. We input it into our as a feature vector, x1 through xd, into our credit approval system, and then out pops an approval or denial decision. It's approved if you call it a +1 example, or so-called positive example, and for denial, it's -1, or so-called a negative example. And so how do we do this? We take our weighted sum. So here we have our summation for I goes from 1 to D, so that's our D many features. And we calculate WIXI, so we're going to take the weighted sum, each feature corresponding to the customer's description, times the respective weight as it from the linear model. And so we sum this WIXI, each one of those terms, for the D many terms, and we take that sum compared to the threshold. Now, if it's greater than the threshold T, we approve this person for credit. If it's less than the threshold T, then we deny this person for credit. So then we can also rewrite our hypothesis, and this hypothesis is one instance of a function from a function class. We can rewrite this as sine of this weighted sum. The sum of I goes from 1 to D of WIXI minus T, our threshold. And so how we arrived upon that, we took the expression here for the approval problem, for example, and then we subtracted T from both sides. And then the sine function, this is SIGN, not the trigonometric function sine as in sine, cosine, tangent. What the sine function, SIGN, does is if the quantity inside the parenthesized expression, if the parameter to this sine function is negative, sine returns a -1. If this term inside of sine, this parameter to sine, is positive, greater than 0, it returns a +1. And so our hypothesis, if you input a particular feature vector x in D dimensions representing the descriptor for that customer of the bank, if you input that x, well, our hypothesis, our current set of W corresponding to the current hypothesis, our hypothesis is going to output a +1. Otherwise, it outputs a -1, meaning that that hypothesis believes that particular customer should be approved or denied for credit. Okay. So how do we arrive upon this? We'll kind of clean this up a little bit. So we're going to take this expression here, sine of our weighted sum minus T, the threshold, and we're going to replace minus T, we did that last time, with a constant W naught. And you can do that because W naught can be any real value, and so it can certainly be a negative number, and it is mathematically correct to replace this minus T with a constant W naught. And so when we do that, this minus T turns into a plus W naught. Okay, so now we're going to make use of the fact that if we multiply any number by 1, well, it doesn't change the value of that number. And so we insert a term x naught, and x naught is just a dummy variable, and its value is fixed to 1. And that does not change the expression of the value of W naught if we multiply it by 1. So we'll just multiply this W naught by this x naught. So x naught is just a dummy variable whose value is a constant 1, and it does not change the value of the expression. And so we get this term here, sine of quantity, this weighted sum, I goes from 1 to D of WIXI, plus now a W naught x naught. So we make an observation, or we made an observation. Here we see the indices of our W naught x naught, that's both 0. And we make the observation here that if we look at the summation, this x naught W naught term looks like another term that we can pull in to this summation. And the reason why we can do that is because of the associative rule of addition. And so rather than adding the first term through the dth term and then taking that sum and then adding W naught x naught, we're going to sum them, fold them into this summation and put them together with the other terms in the sum. And so if we do that, our index of the summation changes from a 1 to a D, and we result in the parameter specified to this sine function as being the sum for I goes from 0 to D of WIXI. And so if we do this now, we can represent this in matrix vector form. And how we'd represent this in matrix vector form is by taking the inner product of vector W with vector X. Now, in this case, our W vector is augmented, right? We started out with W1, W2, W3, up to and including W sub D, and now we have a W naught term. So our new weight vector W is going to have a W naught term, right? So our W here in the sign W transpose X down at the bottom of the slide is the augmented original weight vector with D terms, W1 through WD. We added a W0 term. And likewise, our X vector here is an augmented version of our original feature vector representing all the attributes from the customer application. And so this X vector is augmented with an X0 term, right? And that X0 term is fixed to a value of 1. So this X vector here in this matrix vector form of this hypothesis H of X is going to be X0, X1, X2, up to and including X sub D. Okay. So let's go back to the algorithm we had for searching, and this is called the Perceptron Learning Update. In a series of rounds or iterations, we're going to take a point for which the hypothesis set disagrees with the ground truth labeling. And so here we said that H of X is going to output a +1 or a -1, +1 for approval, -1 for denial, if from the perspective of that hypothesis that this particular customer should be approved or denied for a mortgage. Now, we were given initially, because these X's are historical records, we were given a ground truth labeling, all right, and that was provided for us by the unknown target function, which we talked about in the anatomy or architecture of a learner. And so that means for a given set or instantiation of the weight vectors, we're going to have a different hypothesis, and each hypothesis is going to input a +1 and a -1 or a -1 for each one of the historical customer records. And so for some of those customer historical records, the hypothesis is going to agree with the target function, meaning that the hypothesis, when it outputs a +1, the ground truth was a +1. That person was approved. When the hypothesis outputs a -1, meaning that that customer should not be approved, the ground truth was that the customer was approved. So anywhere that the hypothesis H of X agrees with the ground truth label, that's called a correctly classified point. Everywhere it disagrees, it's called an incorrectly classified point. So here in a series of rounds, we're essentially searching through the set of hypotheses the same way we illustrated before with the line. We're searching for different lines, trying to find a line that most closely agrees with the ground truth labeling. So in this case, we select the hypothesis by some randomization, and then in a series of iterations, we're going to select some point, some customer record, for which the hypothesis disagrees. And you can make that a random choice for which the hypothesis disagrees with the ground truth labeling. Now, once you do that, that's going to be our xi. And so you're going to now update or change this hypothesis to select a new hypothesis or a different value of weights such that you correct for this incorrect decision, right? You correct for that hypothesis. So essentially what this update said, and where we left off, we say W gets the old version of W plus the ground truth label YI associated with that customer record XI, we multiply. So W gets W plus YI XI. And what that does is that changes the hypothesis. When you change the hypothesis, you're basically changing the line. If it were a line in the plane or a two-dimensional linear model, you're changing or switching to the hypothesis under consideration. And the goal is to find or arrive upon, after your series of rounds, to arrive upon some final best hypothesis that most closely agrees with the target function, i.e. that has the minimum number of points for which it is incorrect, i.e. for which it disagrees with the ground truth target function or the ground truth labeling. And so you can think of this line as being a so-called decision boundary, and that's what it's called in the literature. And this line, if you notice here, ground truth, we have our points labeled the blue and our points in feature space labeled the red. Now the red points, those are the negative examples, those customers who were disapproved or denied for credit. And the blue pluses represent the points in feature space corresponding to the customer descriptions, the customer attributes for describing the customer, for which the ground truth was that they were approved for credit. Now you'll see this line here, that line is called the decision boundary because it represents that boundary for all possible customers that can come along, that boundary that defines when you are approved versus when you are denied for credit. And so here you'll see there's a plus point on the wrong side of the line, right? That's an incorrect point. And that's a customer with a certain projection along horizontal, say your annual salary, and projection along vertical axis, which is like the years in residence. So that point, ground truth, was a person that was approved for credit, but for some reason, this particular hypothesis, this purple line, said that that person should be denied. And so when you do this update, essentially what it's doing is shifting or selecting a different hypothesis such that that point is now on the correct side, i.e. it has its correct classification from the perspective of this hypothesis, i.e. it matches what the ground truth is. Okay. So let's take a look at another type of learning. That was so-called supervised learning. And in supervised learning, it all depends on this YI. This YI is so-called supervision, if you will. It's our ground truth labeling. And this ground truth labeling tells you what is the actual outcome for a particular type of customer. And so the goal for the supervised learning is for the learner to engineer some set of weights, some linear combination that is the right linear combination, such that it matches the way this unknown target function assigns these ground truth labels. Okay? All right. So let's take a look at unsupervised learning. And this unsupervised learning will motivate this with an application, and then we will go forward with some of the modeling aspects and some of the tools that we need, and ultimately, maybe not this module, but the next module will implement something. All right, so what is unsupervised learning? So before, we were given the class labels, right? We had these historical customer records representing customers at the bank, and we were given them, and the goal of the learner in the supervised case was to engineer the right linear combination, the right set of weights that agree with this ground truth labeling. Now, sometimes you just don't have these labels, right? You just have data. And if you don't have these labels, the best you can do is compare customers to one another and identify similarities or pattern among the different data points that you have, among the different customer attributes in the case of the mortgage or the credit classification problem. So why do you identify similarities and patterns? Because this allows you to group them together. Now, once you group them together, you say this customer looks a lot like that customer, plus or minus some delta. Now you can make statements about these groups, right? This is immensely useful for lots and lots of applications. So let's talk about an application, and we're going to assume that features describe customer purchases, right? So you go into a supermarket or you go into a department store and you buy a bunch of stuff. You need a way to represent all of the things you bought, your behavior, uniquely as some point in some high dimensional feature space. So let's assume the features that we have are going to describe customer purchases. So here we have a fictitious example, and this is just for the sake of showing you what clustering is, and then we'll revisit this in a more realistic way to show you some of the tools that we need in order to implement clustering or unsupervised learning. So this is our fictitious super duper market, unless we get sponsorship from some real store. But nonetheless, we have a two-dimensional feature space. Now, each point here represents a customer. And what do you do when you're a customer in a store? Well, you buy things, right? And so let's call the horizontal axis a measurement of the amount of post-consumer content, right? The amount of reused paper, so to speak. So here, for example, we have Kleenex. And Kleenex, you know, let's take for the sake of consideration, let's just imagine Kleenex was new paper, right? Made out of new, trees and wood pulp and all that good stuff. And then, an increased amount of post-consumer paper content is napkins, right? Napkins have a little bit more recycled material in recycled paper in it. And then paper towels has the highest. So let's say you have Kleenex, napkins, and paper towels are different types of products that you would buy or could buy, and these have different amounts of post-consumer content, and that's what we're measuring by the position along this horizontal axis. So then let's consider a beverage, right? And let's say, you're going to describe beverages based on the amount of acidity they have. Now, if you're measuring them in terms of acidity, well, let's think of something that has relatively low acidity. And so baby formula has very low acidity, right? Babies can't, newborns or infants can't really digest things that are high acidity, and so baby formula tends to be very low acidity. So then there's milk, and milk has a little bit more acidity, more than formula, but no, still not terribly much acidity, especially if it's like cow's milk that you're drinking. And then, high up on the acidity scale is Coca-Cola. Coca-Cola is very highly acidic, right? So we have on the vertical axis, we have beverages defined by the amount of acidity they have. On the low end, we have baby formula. In the medium range, we have milk, and then on the high part of the range, we have Coca-Cola. So then, let's say we have some customers, and these customers come into the store and they purchase these products. So let's take this customer. This customer has bought a low post-consumer product, Kleenex, and has bought something that's between formula's acidity and milk's acidity, for example. And so each point has a projection in terms of the paper product they buy and the beverage they buy. And you can notice here some customers, when they purchase things, they tend to be more similar to one another. So customers in this second grouping tend to be more medium post-consumer content and medium acidity, whereas customers in this first group on the lower left-hand corner of this graph in this coordinate system tend to be on the low end of post-consumer content and the low end of acidity in terms of the beverage. So as you have lots and lots of customers, you can certainly group them together by comparing each of their features, the post-consumer content feature and their acidity feature for the beverage, and start to say, all right, well, these customers are more similar to one another, and these customers are less similar than one another. And so you can use this to form groupings. So let's say, for example, we're interested in 3 groups, and I'm just going to depict these groups up top here using these boxes, G1, G2, G3, and certainly you would implement these as a data structure, just some kind of list, and you're going to pop in these lists all of those customers as defined by the coordinates based on some assignment to grouping that they have with one another. And so you start out with these 3 groups, and I just selected 3 groups because it looks nice, but you could certainly have 2 groups, you could have 4 groups, you could have 5 groups, all sorts of things, and that's something we'll talk about, what criteria you might employ to decide what is the best number of groups that you should use. So nonetheless, we have our customer data, and each data point represents customer purchase, and then we have 3 groups, and we're going to start out in assigning points to groups. Now, of course, you don't know precisely which things in the beginning belong to which group, which customers, based on their purchase behavior. So you'll just randomize it. You start out randomly. You just iterate through a list of all of these customers, and you say, okay, you flip a 3-sided die, so to speak, using something like the stick-breaking construction, and then you assign, maybe this point gets assigned to group 1, the other point in the same group gets assigned to group 2, another point in the same group might get assigned to group 3. Right? So you make some initialization in assigning points to groups. Okay, so each point in a group has a horizontal coordinate and a vertical coordinate. I'll just say X, Y coordinate value in feature space. And what you do then is you add up the distances between every 2 pairs of points for each group. So you have a number of groups, let's say group 1, all those points that were assigned to group 1, you look at the distances pairwise between those points in group 1, you look at the distances pairwise between the points in group 2, and you do the same thing similarly for the points in group 3. Okay, so if you do that, okay, well, for each group, here we have 3 groups. Now, if we look at this expression, we're going to take each point, the ith point and the jth point, and we're going to subtract the x component for the ith and the jth point, within a particular group, and we're going to subtract the the y value for the ith point and the jth point, and we're going to square them. We care about the magnitude, but not the direction. So we sum them together, and we take the square root, and so we're effectively computing the L2 norm that we discussed before between pairs of points within the same group. So we have here, we have some number of groups. So the outer loop here, the outer summation, the index is I. I goes from 1 to the number of points in group 1. And then we have J goes from 1 to I, right? So here we're looking at all pairs of points in each group, and we're computing the L2 norm between them. So let's take, for example, if we had the following points in group 1, and here these red lines represent the L2 norm, or the straight line distance or Euclidean distance between these points. So we're computing all of these pairwise distances between the points within a group, and then we're adding them together, right? Now this is what our L score is. Now, of course, if you have points that naturally don't belong in the same group, what's going to happen, right? You're going to have points that are much further away. So, for example, if you have a point in group 1, and you have another point in group 1, but the other point in group 1 doesn't really belong. So let's look at this point here in group 1, this other point in group 1. They're very far away from one another. And therefore, the contribution of points that don't naturally belong with one another, that contribution to this L score is going to be very large, and that L measure across all of the groups is going to be very big. Okay. So we have this assignment of points to group, and we start out by randomizing this assignment. And then we take this L score, and we're going to now search for a different assignment to see if we can improve on or make this L score smaller, right? So we're going to search for an assignment that minimizes the sum of L, this expression here, for each group. Can we change the assignment of points to group such that the L score for each group is going to get smaller and smaller and smaller? Does that make sense? I'm so used to saying that. All right. So when you're done with this process, continuing this reassignment and the evaluation of the L scores, reassignment, evaluation of the L scores, the resulting grouping will be relatively compact, and like kinds are going to be grouped together or associated with one another in the same group. And so the resulting grouping then might look as following, and you have these groupings, and we call them clusters. And so here we have the first cluster, we have the second cluster, and we have the third cluster. So now, with the resulting grouping, you have these clusters, and you're going to represent this cluster using the so-called center member of the grouping, right? So now that you have points that you know minimize this L score for each grouping, you then go back and you say, okay, well, rather than representing every single point as that grouping, I'm going to take the centroid, the mean of the X components, this first feature, post-consumer content, and the mean content, and the mean of the Y value, the acidity for the beverage. And so that's going to result in some center, a mean, mu, and that's going to be the center of the set of points, or the typical behavior, if you will, that's going to stand in place as a representative of all of the customers in this particular grouping. Okay? All right. So we have this resulting grouping by minimizing, trying different assignments or changing the assignment until we get a minimum for this L score for each of the groups. And the resulting grouping, the center member, is going to be used to represent the group. Okay. So then you go in and you analyze the groups, right? So again, we don't have labels. And so once you get these optimal groupings, these compact groupings, you then go back in and evaluate these groupings by their center as well as the points in each grouping. You might look at the mean, and you might look at the variance of these groupings to see how compact they are. You might look at the correlation to see how the different types of purchases are dependent on one another. If I have a unit step increase in the post-consumer content, what is the unit step increase in acidity for the beverage, for example, right? So there's all sorts of analyses you can do, but the other thing you do after you analyze them is you give them a name, right? So there's no ground truth label. So you go in to these resulting groupings, and you might say, okay, well, here we have customers whose behavior tends to be on things like Kleenex and things like formula. So I'm going to label these customers as being new parents. When you're a new parent, you buy things that are different from, say, a house with children with children that aren't infants. And so houses with children that are infants, they might buy more napkins, right? And then also buy a lot more milk. As children grow, they drink a lot of milk. Does a body good, as the commercial says. But nonetheless, you might label this second group as being house with children. So then, teenagers, maybe they drink more Coca-Cola or what have you, and they use more paper towels. And so you might go in and label this grouping, a group of customers who tend to buy more paper towels and tend to buy more Coca-Cola or cola-like things, cola-like products. You might call that a household with teenagers. Okay, so why would somebody care about this? Let's say you have a new customer. You go into the store and you buy some napkins. You buy these napkins and then you say, okay, well, let me locate this customer in terms of that one purchase, napkins. So you do that. New customer buys napkins. So based on that purchase, you say, okay, well, what group am I going to locate this customer in? In this simplified example, this new customer bought napkins, so you place them in that group that tends to buy napkin or napkin-like things for their paper products purchase. So then you look at all the other stuff people in this house with children group tend to buy, and then you select something randomly that people in the house with children tend to buy, and that would be milk. So the new customer buys napkins, and as a result, you predict that they're a household with children, and then you print out a custom coupon for milk to get them to make another purchase that you think that they're going to buy. You've now recommended something. And that's how, in a very basic, high-level way, how recommendation systems work, custom couponing and things like that. Now, certainly you wouldn't select any milk to print out a coupon. You would select some milk that maybe is not selling as much, or you have too much inventory, or maybe it's not selling very well. Okay. So there are some issues or framing questions associated with unsupervised learning. One is, what is a good distance measure? Now, we talked about Euclidean distance, but Euclidean distance isn't the only distance measure around. There are lots and lots and lots of distance measures. And in fact, you could spend a graduate degree looking at the structure of distance measures, when they work well, what types, when they don't work well, what types of data they are good for, and so forth. Then also the question of what is the best number of groupings. Right? How many clusters should you assume? Now, I just assumed 3 groupings for the sake of explanation, but there are lots and lots of considerations for what is the optimal number of clusters. So also, how many axes are appropriate for representation? That gets into what is the right feature space representation. How much data is needed to accurately predict the behavior? Because if you have too few data points, well, it might not be as descriptive of what the true customer behavior is. Or maybe you have very few parents with young children, very few new parents. You only have 2 of those examples, and maybe you have 100 of the examples of a house with teenagers. Well, any prediction related to Kleenex, it's not enough data points. Maybe you have retirees, and retirees might buy a lot of Kleenex. It doesn't mean they're new parents. They just buy a lot of Kleenex. And so if you don't have enough data, you're not going to get very high-quality predictions. So how much data is needed to accurately predict behavior? So then what happens when you scale to large data sets? You can't really search for very well through all the different types of assignments of points to groups if you're dealing with many hundreds of millions of data points. So imagine instead of these few points here in feature space, imagine if we had 100 million points and the number of dimensions, features we had was like maybe 5,000, one for each of the products that they sell in a Target store, for example. So how do you scale to large data sets? And then how novel should predictions be? So perhaps, in the case of this person who purchased napkins, all right, well, are you going to predict or recommend what people in this group called House with Children, that we've been calling House with Children, exactly what they predict? Or are you going to kind of, allow it to predict milk plus or minus some amount of acidity? Because, hey, they might like this other type of milk. Maybe it's buttermilk, which is a little bit more acidic. Or they might like something that's a little bit softer. Maybe it's a type of milk that's, treated somehow and it's a lot less acidic. So the other idea is that when you make these predictions, these recommendations, you might want to show them an item that is from a nearby group. They don't know if they like something that they haven't tried yet. So those are some, high-level issues that you might want to consider within supervised learning. And this certainly is not an exhaustive list, but this is just to get you thinking about all sorts of aspects of the unsupervised learning problem. So let's take a look at D-dimensional data. We have this data representation, and of course, for the sake of instruction, for the sake of understanding this, we looked at data in 2 dimensions, but certainly you have some data. And so this data is vector valued, and we have here x1 is the first customer, if we're dealing with customer purchases. X2 is the second customer, x3, x4, up to and including x sub n. Now, of course, if we have D features, the x1 is a point in D dimensions. So we have x11, x12, up to and including x1d. Likewise, notationally, we have x21, x22, x2d. And then lastly, we have the nth data point, xn1, xn2, up through and including xd. So if we have a jth data point, xj, we would label it or write it as xj1, xj2, x dot 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 up to and including xjd. So here, the subscript on the vector x sub j, that's the jth data point, and then here we have the first feature of the jth data point. So that second subscript, if you will, is the feature, where the first subscript is the data point. So xj1 is the first feature of the jth data point. xj2 is the second feature of the jth data point. And lastly, xjd is the dth feature of the jth data point. And so xj is a point in D-dimensional feature space. Okay, so let's go on and look at these cluster centers. We talked about this idea of a cluster center as being this average, if you will, that is representative of all the points that are in a particular grouping that we called a cluster. And so we start out, we select K, some number of clusters or groups that we desire. And so this algorithm will say, okay, well, if you give me K groups, I'm going to put the points that are closest to one another in K different ways. All right, so each cluster is labeled S, and S has a subscript, and that subscript is the cluster number. So you have the first cluster, the second grouping, the third grouping, the fourth grouping, up to and including the kth cluster or kth grouping. So each cluster is noted as S sub 1, S sub 2, S sub 3 in capital S, up to and including S sub K. And so each cluster is going to be a set of points. So a cluster could have 1 point. A cluster could have, 100 points. But if a cluster is empty, we don't usually talk about it because it doesn't exist, right? So if you have n data points and one cluster has most of the points, that cluster can have no more than n minus k minus 1, right? So n minus k plus 1 points, because the remaining k minus 1 points, each one of the other k minus 1 clusters have to have 1 point in it to be a cluster, okay? So each cluster is going to have a center, and we're going to call this cluster center the so-called center point. That's going to be the cluster's mean, right? And so the cluster center is going to be computed as the mean data point, right? So it's not a real data point. It's just the resulting position in feature space that arises from taking the mean of the first feature and the mean of the second feature. Okay, so we start out and we select the number of K randomly initialized cluster centers, and then we assume all of the points in each grouping or each cluster, we're going to take the mean, right? So the mean of the first cluster associated that represents the first cluster is going to be mu sub 1. The mean that represents the second cluster is going to be mu sub 2. The mean that represents the kth cluster is going to be mu sub k. And so likewise, going with that same scheme for how you talk about features, well, mu sub 1 is going to be a vector in d dimensions, and mu sub 1 is going to consist of mu 1, 1, mu 1, 2, mu up through including mu 1d. Likewise, mu 2 is going to be mu 2, 1, mu 2, 2, up to including mu 2d. And then for mu k, we're going to have mu k1, mu k2, up to and including mu kd. And so here we have the ith cluster center, or the ith cluster mean, mu sub I, is going to be described mathematically as mu sub I1, mu I2, up through and including mu ID. Now here, the subscript represents which cluster center it is. So mu sub I is the ith cluster center. It's the mean of the ith cluster, S sub I. And mu I1 is going to be the first feature of the ith cluster, of the ith data point. Well, we call it data point because the cluster center is exactly a data point. But this mu I1 is going to be the mean of the first feature of all the data points in the ith cluster, right? So you can think of it as the first feature of the ith data point, where the ith data point is just the mean or the center data point. Likewise, we have mu ID is the dth feature of the ith data point. That would be the mean of the dth feature for all of the data points in the ith cluster. Okay, so the ith cluster center corresponds to the set of points or the cluster S sub I. So S sub I, the ith cluster, or the ith set of points that are most similar to one another, has a center mu sub I. Does that make sense? Okay. So we also, that's the center, but we didn't talk about the data points in that cluster, right? So Si is the set of points, mu I is the mean of the set of points, where xj is going to be used to represent the points themselves from which you compute mu sub I, the center, okay? So we have for each cluster Si, we have a center, mu sub I, and we have a set of points xj. Okay, so let's take a look now at distance measure. And so you're given a set of data points associated with a particular cluster, and your data points, you have n many data points. No, it's not the same cluster. You're given a set of data points, and we call those data points x1 through x big N, right? And so we have x11, x12, x1d, up through and including xn1, xn2, xnd. And so here, each of these data points, going by the scheme that we talked about before, for the jth data point, xj, that consists of the first feature, the second feature, the up to and including the dth feature. So we have features for point xj, we have features xj1, xj2, up through and including xjd. So now we select a number of randomly initialized cluster centers, and each cluster center point or mean is defined, right? We just take the mean of all the features associated with all the points in that cluster. Okay, so now given any data point, right, and a given cluster center, what do we do? Now we're going to do that reassignment. So you have all your data points, the jth data point. J could be 1, J could be 2, J could be n, for each of those big N many data points. And we have the cluster centers. We have k of them because we have k clusters. So we can measure now the distance between a data point and a cluster center. We just take the L2 norm between each of those big N many data points and our k cluster centers. And so something's going to happen, right? You're going to get a distance, and you're going to reassign those points to the cluster for which they are closest to the center, each of these mu's. Does that make sense? Okay, so let's take a look at this. We can take the L2 norm between each of these data points and these k cluster centers. So how do we do this? We take the distance between each of the n many data points and each of the k many cluster centers. We have big K of these cluster centers. So mu sub I goes from 1 to big K. And we have big N many of these data points, j goes from 1 to big N. So we can measure the distance, or the L2 norm, between each data point and each of the cluster centers. And so when we do that, okay, well, what are we doing? We're taking the square of the difference between the first feature of each data point, xj1, and each cluster center mu I1, and then we're doing the distance, we're adding to that the distance, the difference squared between the second feature of each data point and the second feature of each cluster, and the third feature of each data point and the third feature of each cluster, up to and including the square of the difference between the dth feature of each data point and the dth feature of each cluster center. So we do that, and essentially what we're doing is we have each of our cluster centers, mu sub I, we're literally taking the distance between each of the data points and each of the cluster centers. So now what happens is that some data points will be close to a cluster center and some data points will be far from a cluster center. You're going to now reassign points to clusters based on how close they are, i.e. to the closest cluster center. Okay, so this reassignment has a name. It's called Lloyd's Algorithm, and Lloyd's Algorithm is actually an approximation for an exhaustive search. Okay, so you start out and you randomly select your cluster centers. You randomly select them. Some people advise, instead of randomly selecting them, you randomize them to select the actual some of the points to be the cluster centers. But you randomly select in some fashion what your cluster centers will be for your K clusters. So if we had K equals 3 clusters, we'd randomly select 3 cluster centers in the beginning, and then we're going to improve them by replacing them with the actual means of the groupings that we find. So then you randomly assign each of your n many data points to your groupings, to your clusters. So you randomly select your cluster centers, and then you randomly assign your points. You're not really computing actual means, and you're not really doing actual assignments at the initialization. Okay, so now you iteratively minimize the following expression. Now, what this expression is doing, it has 2 parts. The first part, if we look at the outer summation, that index little k goes from 1 to big K. That's going to iterate over each of the clusters. So what is it saying? For each cluster, for each grouping, SI, each set, we're going to take each of those data points from a particular grouping, and we're going to sum the L2 norm squared, the distance between each of those points within a cluster and the cluster center, right? So that's saying, what is the distance between each point in a cluster and the cluster center, given this initialization? And you're going to add that up for the first cluster, the second cluster, the third cluster, and so forth, up to and including the Kth cluster. So you're going to minimize this expression, and when you have the right assignment and the right cluster center, as a result of changing the assignment, the cluster centers are going to change because the cluster centers are going to be computed by the mean. This expression, outer sum plus inner sum of this square of the L2 norm, that's going to be minimized. Now, of course, you could search all possible assignments, right? But that's not going to be feasible. And so the best thing you can do is an approximation where you're going to iterate between one of 2 alternatives. Now, the reason why this is too difficult is because for each data point, you have each of the n many data points, you have k choices as to which cluster you can assign them to. So you have the first data point. You have 3 choices if it's k equals 3 clusters that you can assign it to. The next one, you have 3 choices. The next one, you have 3 choices. With arbitrary k clusters, for the first data point, you have k choices. The second one, you have k choices. The third one, you have k choices. And the nth one, you have k choices. Now, if you have each of these choices for these n many data points, all the possible assignments that you can have of points clusters is going to be k times k times k times k n many times. So this is a large number of different assignments that you can search, and you can't possibly exhaustively search all possible assignments for the optimal that minimizes this expression. It takes too long to do that. And so it takes too long to do that because you have to test each assignment and then compute this score to see which one gives you the minimum. And so for just n data points, right, and k clusters, it's k to the n power, and this is a so-called exponential runtime, and that's not feasible. It blows up with just very small numbers. So we have k choices for each of the assignments of the n many data points clusters. So that's k times k times k times k multiplied by itself n many times. That gives you total of k to the n power many choices, where n is the number of data points you have. So imagine if you had customer records with 100 million data points, that would be k to the 100 million power, which is absolutely huge. Okay, with only 3 clusters and only 10 data points, which is a trivially small problem, you have 3 to the 10 solutions, which is already starting to get big in terms of the number of solutions you search if you're trying to minimize this expression, which is the distance between the cumulative distance between points in a group and their cluster center summed across all of the clusters. So instead, we approximate by doing what's called alternation. We fix one quantity, the assignment, and then we update the mean. And then we reassign based on those, and then we update the mean. And so what we're going to do is we're going to update the centers, right? And we're going to update the centers by basically taking the average of each of the features for the points within a cluster. So we have for every xn data point within the kth cluster, we're going to sum all of those feature-wise values for each of those d-dimensional data points in that grouping, and then we're going to divide by sk, 1 over the size of that set. That's going to be our mu k. So literally, we're going to take the average of the first feature, the average of the second feature, average of the third feature for each of the d-dimensional data points in that particular grouping. And that's going to be our update for our value of the cluster center. So then after that, we fix, once we compute those updated cluster centers, we hold that constant. We don't change them. And then we loop through all the data points and we reassign them. And how do we reassign them? Well, each of those clusters are going to change. And it's going to change to include xn if xn, the distance between xn and the kth cluster center, is smaller than the distance between xn and all the other cluster centers. And so we reassign, fixing the cluster center at this point, and then we take the assignment, keep it fixed, and update the cluster center. Then once we update the cluster center, we then fix the cluster center, change the assignment. Then we fix the assignment and change the cluster center. And we keep alternating until this expression, we get very few small change in the value of the cluster center, or conversely, you could trigger the halting of this algorithm by no change in the assignment, either or, and then you stop. So you fix one value, and then you update the assignment. Then you fix the assignment, and then you update the center. Now, this is called the expectation step, and this is called the maximization step. But we'll save that further discussion on expectation maximization for later. But Lloyd's algorithm is an alternating technique that gets beyond the infeasible complexity of searching for all possible assignments by fixing one quantity and solving for the other quantity and just alternating back and forth between the two. Okay? All right. So you do this until there are no more changes, and that is Lloyd's algorithm, and it gives you a decent approximation to the optimal of the k to the n power different assignments that you can search. Okay? All right. So with that, I will end there. And again, please watch the YouTube video. You are at the following URL that talks about Kmeans clustering and how it works. I posted on Blackboard a PDF. There's the URL to the PDF, but it is linked on Blackboard already. You'll be reading pages 490 to 494 and 496 to 506. So I will see you on the live session, and we will end there. I will see you on Tuesday.